In the previous lecture on angular momentum, you have seen the problem of eigenvalues and eigenfunctions of the operator Lz. Now today we will find the eigenvalues and eigenfunctions of the operator L square. Actually, you know L square is also a very important angular momentum operator, and the eigenvalues problem of L square is most important in quantum mechanics and its applications. So to get the eigenvalues and eigenfunctions of the operator L square, as usual, we will first of all write the eigenvalue equation of this operator, and we will solve the problem in a spherical polar coordinate system, because I have told you earlier that while discussing the problem of eigenvalue and eigenfunctions of the angular momentum operator, the most convenient form of the operator is in spherical polar coordinates, not in Cartesian coordinates. So we will solve the problem in spherical polar coordinates. So let us write first of all the eigenvalue equation of the operator L square. You know, if we consider that psi of r theta phi is the eigenfunction of this operator L square, then the eigenvalue equation of this operator may be written like this. We will simply operate the operator L square on this eigenfunction psi of r theta phi, and then you know we will get the eigenvalue of this operator, which I have denoted by the symbol lambda here, and the same eigenfunction. So L square psi of r theta phi equal to lambda times psi of r theta phi. This is the eigenvalue equation of the operator L square. As I have told you that in this equation, this psi of r theta phi is the eigenfunction of this operator L square, and lambda is its eigenvalue. Our aim is to find both of these. That is, first of all, we will see how the eigenvalue lambda will be found, and then we can also see what will be this eigenfunction r theta phi of this operator L square. So to obtain the eigenvalue and eigenfunction of this operator L square, first of all, you have to remember what is the expression for the operator L square in spherical polar coordinates. As you have studied this in earlier lecture, that the operator L square in a spherical polar coordinate system is defined like this. I have already derived this operator in the previous lecture, and so you can remember it. And I have told you that the derivation of this operator L square in a spherical polar coordinate is not so important as we should remember it. In fact, remembering this operator is more important, because in numerical problems and also in theoretical discussion you always need this expression. So you can remember L square in a spherical polar coordinate system is defined like this. This is minus h bar square times 1 over sine theta del del theta sine theta del del theta plus 1 over sine square theta del 2 by del phi square. This is the expression for L square operator in a spherical polar coordinate system. Now use this expression of L square in this equation 1. Then your eigenvalue equation will become in this form. You can see, instead of L square in equation 1, we will now write minus h bar square 1 over sine theta del del theta sine theta del del theta plus 1 over sine square theta del 2 by del phi square. And this operator will be operated on the function psi of r theta phi. And then you will get lambda psi of r theta phi. So this is the eigenvalue equation of this operator L square in a spherical polar coordinate system. Now in the earlier lecture you have seen how we can find the eigenvalue and eigenfunction of the operator Lz, and what are its eigenvalue and eigenfunction, you have already seen. One thing I have discussed in the lecture on commutator algebra, that if two operators commute, then definitely those two operators have a common set of eigenfunctions. And you have seen in commutator algebra that these two operators L square and Lz commute. It means commutator of L square and Lz is equal to 0, which means L square and Lz commute. And if L square and Lz commute, you know they will have a complete set of common eigenfunctions. So if you want to know the eigenfunction of operator L square, you have to start with the eigenfunction of the operator Lz, which you have already obtained in the previous lecture. You can remember. So before going through this video, you must watch the video on the calculation of eigenvalues and eigenfunctions of the operator Lz. If you can remember, you have seen in the previous lecture that the eigenfunction of the operator Lz is defined like this: psi of r theta phi equal to a of r theta e raised to the power I m phi. You have seen. Actually here the a is a constant which is not a universal constant. It is a function of r and theta, but it is independent of phi. In this sense, you can say a is a constant which is independent of the variable phi, but it depends on r and theta. In fact, in this equation, you know m is an integer. It may be a positive integer or negative integer or even 0. Now, if your aim is to find the eigenfunction of the operator L square, and in this equation 3, we have defined the eigenfunction of the operator Lz, then there is only one task, only one problem to you. You have to find the form of this constant a of r theta in such a way that this function psi of r theta phi then becomes the eigenfunction of the operator L square. Again, I am telling you that this equation 3 defines the eigenfunction of the operator Lz. And if our aim is to find the eigenfunction of operator L square, only you have to find the form of this quantity a of r theta in such a way that this psi of r theta phi now becomes the eigenfunction of the operator L square. So for this, let us use this equation 3 in this equation 2, that is the eigenvalue equation. What you will do? We will simply replace this psi of r theta phi by this expression, that is a of r theta times e raised to the power I m phi. So you can see here. In fact, when we will replace this psi by a times e raised to the power I m phi, then that psi will be here, that is before this del operator and before this del square. And as you know that a is a function of r and theta, so here a will be in first term, a will be differentiated, but e raised to the power I m phi will be treated as constant because this is just a partial differentiation. And similarly in second term, as the partial differentiation is with respect to phi, so e raised to the power I m phi will be differentiated, but a will be treated as a constant. So see, you can see here, in the first term I have differentiated this a because a is a function of theta, and we have taken this e raised to the power I m phi outside of the differential operator. But in the second term, since the differentiation is with respect to phi, so e raised to the power I m phi will be differentiated, but a, which is not a function of phi, is outside of this differential operator. And in RHS, psi has been again replaced by a e raised to the power I m phi. I hope you have understand this step. Now let us see. The first term is as you can see here, and in second term what we will do? We will simply differentiate 2 times the function e raised to the power I m phi with respect to phi, because there is a second order partial derivative here. And after differentiating e raised to the power I m phi 2 times with respect to phi, you will get minus m square e raised to the power I m phi. So the second term is now minus m square a over sine square theta e raised to the power I m phi. And RHS is at it, as you can see here. Now, by this factor minus h bar square, you can see I have divided by this factor to the RHS. So here there is minus lambda over h bar square. And as you can see inside this square bracket, this factor e raised to the power I m phi is present in both terms. So I have taken this factor e raised to the power I m phi as a common factor and nothing else. So you can understand this step. Now, as e raised to the power I m phi is present in both sides, so they will cancel out and now bring this term in RHS, which is minus lambda over h bar square a in LHS. So that will become plus. And a is present in this term and also in the second term inside this square bracket. So I have associated these two terms by taking this a as a common factor. And so your equation becomes 1 over sine theta del del theta. Now, one thing I have done here for convenience, which you will see later on. In fact, in our equation there is sine theta, but I have written here sine square theta over sine theta. After simplification, this will be simply sine theta. So this sine theta may be written like sine square theta over sine theta. This is done for convenience, which just we will see now. So this is our eigenvalue equation. Now, to transform this equation into a standard differential equation, this is a differential equation whose solution you cannot think in the standard form. First of all, we have to change this differential equation into a standard differential equation, and then we will see what will be the solution of this differential equation. So to transform this equation in the form of a standard differential equation, let us make a substitution, or we change the variable theta in another variable x. So let us define x equal to cos theta. We consider, and if x is equal to cos theta, you can see what will be dx. This will be minus sine theta d theta, minus sine theta d theta. Or you can say that this sine theta d theta will be equal to minus dx. And as x is equal to cos theta, so sine square theta, this will be equal to 1 minus cos square theta, and this is 1 minus x square. Now let us make the use of these relations in our equation 4. You can see here there is sine theta del del theta. So instead of this sine theta del theta, we will write minus del x. And again inside the bracket you can find sine theta del theta is present. So this will be also minus del x. So in outside there is minus del x and inside the bracket there is again minus del x. So that minus minus will become now plus. So you can omit the minus sign and this sine square theta will be replaced by 1 minus x square. So making these substitutions in equation 4, you can write therefore equation 4 may be written as. How we can write this equation? You can easily see. This will be, you have seen, this will be del x sine square theta, and that sine square theta will be 1 minus x square, and del a by del x. You can see. And plus, see the equation, lambda over h bar square minus m square by sine square theta. And sine square theta, this is 1 minus x square. So this is lambda over h bar square minus m square by 1 minus x square times a, and this is equal to 0. This is equal to 0. Now let us simplify a little bit the LHS of this equation. You can see inside the first square bracket there is a product of two functions. The first function is in fact 1 minus x square. This is in fact x square. You can see this is x square. And the second factor is del a by del x. So we will follow the rule of differentiation of product of two functions in this first term, and you can see this will be 1 minus x square times del 2a by del x square. Now we will differentiate this first factor, and after differentiation you will get minus 2x. So this will be minus 2x del a by del x, del a by del x, and plus lambda over h bar square minus m square over 1 minus x square times a equal to 0. Now, as you know, for the purpose of differentiation and integration, this r is treated as a constant. R is treated as a constant because we have seen that the constant a is a function of r and theta, but here the differentiation is with respect to x, and x depends only on theta, not on r. So in this condition, since a is just a function of only one variable, that is theta, so instead of this partial derivative, you can write the ordinary differentiation, and therefore you can treat that a is only a function of x, and therefore the above equation may be written like this. This is 1 minus x square, and instead of partial derivative, now we will take the ordinary derivative, that is d2a by dx square, and minus 2x dA dx, and plus lambda over h bar square minus m square over 1 minus x square a equal to 0. And say this is your equation 5. Let us say. Now see this equation. If you have studied the special function, particularly the legendre equation and associated legendre equation in my videos on a special function, then you can recognize this very important differential equation. Can you recognize? Definitely you will recognize it, because you have already studied these things in my course on mathematical physics on a special function, that this equation 5 is nothing. This is simply the associated legendre differential equation. And if this integer m will be 0, then this equation 5 will become legendre equation. But if m is not 0, then this equation is known as associated legendre differential equation, which you have discussed in very detail in my course on mathematical physics on a special function. So you can say this is associated legendre equation. Legendre equation. Now see the form of this equation. If this variable x, you can see here, tends to 0, or in other words you can say that theta is equal to 0, because when theta is 0, you can see here this x will be cos 0 and cos 0 is 1. So you can say that if x tends to 0, that is theta tends to 0, then 1 minus x square will tend to 1 minus x. If x does not tend to 0, but x tends to 1, not 0. Theta tends to 0. X tends to 1, that is theta tends to 0. Then 1 minus x square will tend to 1 minus 1, that is 0. And if 1 minus x square is 0, you can see the form of equation that this m square over 0 will become undefined. So in this condition, the solution of this equation will diverge. But even in this condition, for any value of theta, when theta is either 0 or any value, the solution of this equation will not diverge, but for that there should be a satisfaction of a particular condition. So if x tends to 0, that is theta tends to 0, then this is 0, and the solution of this equation will diverge unless there is a condition when the solution will not diverge, unless this quantity lambda over h bar square, this is equal to a product of two successive non-negative integers. I am not telling positive integers but non-negative integers, because that integer may be even 0, and you know 0 is neither a positive number not a negative number. So you should say non-negative integers. It means when lambda over h bar square will be equal to product of two successive non-negative integers, then for any value of theta or any value of x, there will be a finite solution of the associated Legendre equation, that its solution will not diverge. But for that, this quantity lambda over h bar square must be equal to the product of two successive integers. So let lambda over h bar square is equal to L into L plus 1, where what is L? L equal to a non-negative integer. Non-negative integer. Non-negative integer. So when this lambda over h bar square will be equal to the product of two successive non-negative integers, only then the solution of this associated Legendre differential equation will not diverge. It will have a finite solution for any value of theta or any value of x. So definitely for obtaining a finite solution of this equation, we must have lambda over h bar square equal to L into L plus 1. And so you can say, what will be your lambda? Lambda will be equal to L into L plus 1 times h bar square. Times h bar square. And as you know that this lambda is what? Lambda is the eigenvalue of the operator L square. So you can see we have obtained the eigenvalue of the operator L square, and this is a very important result and you should remember it. In fact, in other branches of physics like atomic physics, we directly write that L square is equal to L into L plus 1 into h bar square. Or we simply say that L is equal to a square root of L into L plus 1 into h bar. We also write like this. In fact, here this L must be greater or equal to modulus of m. Must be greater or equal to modulus of m. M may be negative, but L, you know, this is non-negative integer, so it cannot be negative, but L will be what? L can be 0, 1, 2, 3, and so on. And so on. So by substituting the different values of L, you can find what will be the eigenvalues of the operator L square. By substituting the value L equal to 0, 1, 2, 3 and so on, you can write its different eigenvalues. So eigenvalues of L square R. What will be the eigenvalue? When we will put L equal to 0, you can see that lambda, or you can say L square, will be equal to 0. When L is equal to 1, then lambda or L square. What will be this? You can see this will be in fact 1 into 1 plus 1 into h bar square. that is 1 into 2, that is 2. That is 2h bar square. When L equal to 2, lambda or L square will be equal to what? This will be 6h bar square, and so on. So you can see the eigenvalues of the operator L square are actually discrete. It has not continuous values, but the eigenvalue spectrum of L square operator is just a discrete spectrum. So after getting the eigenvalues of this operator, now we will focus to find the eigenfunction of this operator. And for this, let us see again this equation number 5. As you know, this equation is nothing. This is simply the associated Legendre differential equation. And you know, you have studied this in a special function, that the solution of associated Legendre differential equation is simply the associated Legendre function or the associated Legendre polynomial. So we will write the solution of that equation 5 in terms of the associated Legendre function. So solution of equation 5 is associated Legendre function. I am not giving any detail regarding this associated Legendre function because you have seen these things in very detail in the previous lecture. And this Legendre function, you know, is denoted by the symbol PLM of x, or you can say PLM cos theta. PLM cos theta. In fact, I have discussed this function in mathematical physics in very detail, but for your convenience, I am just defining it here. PLM of x. You have seen these things in the course on a special function, that this is equal to 1 minus x square to the power mod of m over 2 and d mod m dx mod m PL of x. And what is this PL of x? You know, this PL of x is called Legendre function. This is known as Legendre polynomial, you can say. This is Legendre polynomial. I am not giving any detail of this associated Legendre function and Legendre polynomial. For this, if you want to go again the detail of these two functions, you must watch my video on Legendre polynomial in the course on a special function in mathematical physics. Now, as I have told you, that equation 5 is simply the associated Legendre equation, and so its solution will be associated Legendre function. So we will write now the solution of this equation by multiplying the Legendre associated Legendre function by appropriate normalization factor. So solution of that was equation 5 is given as you can see, the equation is in terms of the function a, so its solution will be a, and that a is just a function of x. So you can write a of x. Now we take an arbitrary constant, let us say b, and the associated Legendre function PLM of x, and this is actually the what will be the equation number? This will be equation 6. Now you can see that this PLM of x, as you have seen, this is associated Legendre function or polynomial, and this b is an arbitrary function of r. B is an arbitrary function of r. Why it is an arbitrary function of r? Because you know this PLMX, this is only a function of theta, but a is a function of r and theta both. So PLM of x, this contains the variable theta, but r is not contained. So definitely this b will be a function of r. And so since it is an arbitrary function of r, so you can replace this b by, in fact, a function of r. Therefore you can write now the quantity a of r theta, this will be equal to an arbitrary function, let us say f of r, and PLM of x, and x, now you can write x equal to cos theta, we have seen. So this a of r theta is equal to this much, and you have obtained this by the solving the associated Legendre equation. Now after getting this value of a of r theta, as I have told you earlier, that the eigenfunction psi of r theta for Lz and that of for L square will be same. Only we have to find the appropriate form of a so that the eigenfunction for Lz becomes the eigenfunction of L square, and we have obtained that form. This is the form of a of r theta, which when you will substitute in the expression for eigenfunction of Lz, then you will get actually the eigenfunction for the operator L square. So you can see the eigenfunction for the operator Lz was what? This was defined in this equation 3. Psi of r theta phi is equal to a r theta times e to the power im phi. And here we have obtained the form of a r theta, and now when you will substitute that value of a of r theta in this equation 3, then this function psi will be called the eigenfunction of the operator L square, and that will be also the eigenfunction of Lz. It does not mean that that is not an eigenfunction of Lz, because you have seen L square and Lz both commute, so both will have a common set of eigenfunction. So that will be the eigenfunction of both the operators L square and Lz. So thus the eigenfunction of L square and also of Lz, are psi of r theta phi equal to a of r theta, and a of r theta is this much. So this will be f of r PLM of cos theta times e raised to the power I m phi. These are actually the eigenfunctions of the operator L square. Now, the product of these two functions, that is PLM of cos theta times e raised to the power I m phi, in fact, this product with a proper normalization constant is known as spherical harmonics. And so, we can replace this factor by the spherical harmonics. So, you can say the functions PLM of cos theta times e raised to the power I m phi with proper normalization factor are called are called spherical harmonics. Spherical harmonics. Spherical harmonics. And this spherical harmonics are denoted by the symbol YLM theta phi. You may also write this symbol like this. This is YLM theta phi. Both of the symbols are permitted. So either you can write these numbers L and M as subscript, or M as superscript and L as subscript. You may write it like this. Both of these symbols are permitted. So if you will replace this product PLM cos theta e raised to the power I m phi by the symbol YLM theta phi, which is spherical harmonics, then the common eigenfunctions of L square operator and the LZ operator can be written in terms of this spherical harmonics. And in case, let us see what will be that. So therefore, the common eigenfunctions of L square and LZ are, you may write like this: psi of r theta phi equal to an arbitrary function of r f of r and ylm theta phi. ylm theta phi. So this is actually the eigen function for the operator L square. Say this is equation B. Now there are several situations when the eigenfunction of the operator L square is independent of R. So if psi is independent of R, then we simply write psi of theta phi, and that psi of theta phi will be equal to some arbitrary constant. Let us say there is a constant C, which is actually normalization factor, and YLM theta phi. Or in simple way you can say that when actually psi is independent of R, then this spherical harmonic is actually the eigenfunction of the operator L square and Lz. In fact, in most of the applications we see that the eigenfunctions of the operator L square and Lz are simply the spherical harmonics. Now we have used the term spherical harmonics, and you can see in the standard textbook the different values of this spherical harmonics. For your convenience, I am writing here some of the values of this spherical harmonics, but in a standard textbook you should see the different values of this. So some of the value I am writing here. You can see YLM theta phi. What will be its values for different values of L and M? I am writing, for example, some of the values here. You can see Y00, 0. It means L is 0 and M is both are 0, theta phi. You should remember it. This is equal to 1 over root 4 pi. Y 10, 10, theta phi. This is equal to root over 3 over 4 pi cos theta. Y1 plus minus 1 theta phi. It means L is 1 and M is plus minus 1. This is equal to minus plus root over 3 by 8 pi e to the power plus minus I phi sin theta. In this way, you can remember some of the values, and studying the standard textbook, you should see how these values are obtained. So in brief, you can say that the eigenfunction of the operator L square and Lz are nothing. They are simply the spherical harmonics. So I hope you have understand the calculation for the eigenfunction and eigenvalues of the operator L square, and these eigenfunctions are also of the eigenfunction of Lz. And remember the eigenvalues of the operator L square, because you will find its application in particularly in atomic physics, nuclear physics, and at several places.